Good morning, Bob Clark with ASI Group. I'm going to apologize right up front because there's pretty much everybody in this room is far more technical oriented than I am. So excuse me if I do make a few little mistakes with specific frequencies that are being used, number of beams, that type of thing. I am going to round it out a little bit. My background is civil engineering and as a diver more than the ROV side. And I think with ASI, the only reason I'm the ROV operations manager is because at the time when they hired me, I was the only one who knew how to spell ROV. So, and I've just stayed with it ever since. It's been very, very interesting. As mentioned, ASI, we're based up in St. Catharines, Ontario, and that's just because that's where the boss lives. That's the only reason. We do work internationally. One of the things that ASI decided to do was to get into the long tunnel and pipeline inspection business. Really, that came about because of zebra mussels and quagga mussels infesting the Great Lakes many years ago. So they would dive at the intakes, dive into pump wells, and then what was in between. So that started the whole niche market for ASI back in the 90s, actually. So as you can see, we've developed quite a track record. We do have the longest tethered systems in the world, and we do work with Woods Hole Oceanographic with AUV systems as well, again for tunnel inspection work. So we operate, the vehicle we're going to be talking about is 10 kilometers long, the tether, or 6 miles, and we have other systems with 5 kilometers, and I'll be wrapping up with our smaller vehicle, the Seabotics vehicle, which is now part of the Teledyne Group, and that operates with 2.5 kilometers as well. We do have a very strong background with sonar systems. Back in the early 2000s, we were doing point cloud data with very high resolution. This was an in-house built system. Since then, obviously, there's more products on the market now, and we've brought in the BV5000 on several inspections to do high density and high level point cloud work. And actually, in some of those, were very small diameter shafts as well. So the product that we're able to deliver is, all the points are geo-referenced, so they do have XYZ coordinate values to them, and used not just from an inspection point of view, but also to do reverse engineering. A lot of the inspection work that we do is to go find out why something is damaged or not working, and then to be able to provide that 3D model to the engineers and the owners so they can engineer and design a repair. We work with lidar systems as well. We have a system which we call ABYSS, which is above and below inspection system. So here we have lidar data, which is on the inspection platform, or collected from laser scanners on the inspection platform, merged with the sonar data. They're all co-located, so everything is being collected in the same vertical plane as we go through the tunnel system. And this is for aqueducts where we have an air gap, basically. So below the water we're collecting acoustic information, above the water we're collecting light-based information. The system also had multiple cameras on it, so we were photographing everything as we went through. So it's a real, as mentioned yesterday, a fusion of data types. So now we've worked with sonar systems, collecting point clouds. We've worked with LiDAR systems. Now we've been asked to compare a LiDAR survey with survey to be done underwater. Now they're starting to push things. And as mentioned, we're a little bit ahead of our time. But we certainly appreciate a challenge. So the client had gone through, a tunnel had collapsed, they did a complete repair, did a LiDAR survey, and instead of having to dewater all the time, they wanted to be able to have an ROV go in, so they would maybe shut down for short periods of time, go in and basically replicate a LiDAR scan, but they want it done underwater. So we said, sure, no problem. This is where it all started from. It's down in Chile. There's actually 2 tunnels, part of the system, and it's called Run of the River. So there's no large dams or reservoirs. What they do is upstream of the river, there's a small reservoir collection area, and then they drill and blast a tunnel that runs parallel to the river but stays reasonably flat grade. And then at the end, then they drop it back down into the river, generating power at that point. So this tunnel, we'll call it HLC, because my Spanish is terrible. So we'll call that one HLC, and this one is HLH. HLH starts right at the end of the last tunnel. That one's 9.4 kilometers, this one's roughly 18 kilometers. So we have our system with 10 kilometers, so this one we can do in one shot. We'll do that, come back out, and this one we actually go in from both ends and then overlap in the middle. The distance part, we're used to that. We had gone 10 kilometers back in the late 90s, and we still hold that record. But it really was being able to replicate that type of thing to get that comparison with the LiDAR data. Zero visibility, it's just a very high sediment load. Anytime it rains, then they just get all the runoff. There are no trees or anything to absorb the moisture, so everything goes into the reservoir and into the rivers. So in fact, we don't even turn the cameras on. We did that once just to see what we would see, and all we saw was brown, and we were right up against the wall. So everything was going to be done acoustically. We're in a confined space, so you can even hear the little echo in this room. You can imagine trying to do acoustics inside of a rock tunnel. It's going to be an issue. Multiple devices from multiple suppliers. At the time, there was Reson, BlueView, we had Tritech equipment on there, we had CDL equipment on there. So trying to integrate things from different suppliers was going to have some difficulty because everybody's going to be pointing the fingers at somebody else, and trying to get rid of all that multipathing issues. How are we going to deal with multiple suppliers? Physical integration of all these things onto one vehicle. We need that. We need real estate. We need a large enough vehicle to be able to accommodate that, and sufficient power to drive everything as well. The operation, now we're going to be in zero visibility, and we're going to be running 10 kilometers out and having to inspect everything. The requirement was actually to find anything, I believe it was 4 inches and bigger, because the intent is that if we get small rocks coming out, that will be an indication that sooner or later there's going to be big rocks coming out, and then they can do more of a planned maintenance as opposed to emergency call-out type of thing. The quality of the data acquisition, as I mentioned, those were the parameters, and now we're having to compare that with LiDAR data. Well, the LiDAR data has got pretty good resolution, and we are being challenged to match that. They gave us a bit of leniency. Instead of having to be 1 millimeter accuracy throughout the whole tunnel. They cut us a bit of slack, and we could do about 12 millimeters, so half an inch. We had to be able to map everything within half an inch. Many of you who do the hydrographic survey side, using one or even dual heads, that's a lot of data. Now we're going to be running through a tunnel, trying to cover 100% of the tunnel and acquiring all that data. And this was going to be new for us. We do hydrographic work, but so that helped with the ROV side. There was a bit of dialogue, but everybody just kind of started rolling their eyes. Historically, we've been doing the long tunnel stuff since the mid-90s. Historically, you go in with a scanning sonar profile, do a scan, move along, do a scan, and we would stabilize the vehicle just to make sure that the cross-section was valid and that there wasn't any movement. With INS systems, yeah, you can put the INS on and then just keep corkscrewing through the tunnel, and then being able to bring all that back and correct it, but we're going to miss things, especially with that 4-inch requirement. So ideally, what we'd like to be able to do, instead of corkscrewing through the scanning system, is that we'd like to be able to use a multi-beam system and fire off, preferably all the way down the tunnel instantaneously, so at least we would be sure that that cross-section is relative. It's all relevant with itself. So the solution was, well, we'll get 3 multi-beams and put them all on the same vehicle, and that'll give us that 360-degree coverage. So what we decided to do, we did do the market research and everything, and the 7125 AUV system was going to be the best. Going through and collecting multi-beam or point cloud data, that's great, but if we miss something, because maybe the point would be here or here, but we would miss this small rock in the middle, we wanted to get that full imaging. So the BlueView sonars, they'll ensonify 100% of the target area in front, so that ended up being the system of choice. At that time, I believe the M900 had just come out, and so we said, sure, we'll take 3 of them and integrate them all at once onto the machine. We did it a little bit differently. It's not just the forward-looking, but we took 2 of the sonars and then rotated them up 90 degrees so we could image the tunnel walls all the way down as well. part of the requirement's not just looking for materials and such on the floor, but also to see if there were cracks and what was going on with the tunnel walls as well. Being able to identify cracks with sonar is difficult, and a lot depends on the geometry. It's as simple as that. It could be a very wide crack but longitudinal. We wouldn't see it, but if it is perpendicular or at least at an angle to the sonar beam, then sure, it's going to stick out a little bit. Now we're going to take all these sonar systems, which have high bandwidth, high demand requirements, and put them onto a vehicle. Well, from my experience, as soon as you start building something, the client's going to want more sensors, more power. So we just took the best machine that we could find that would meet our general inspection requirements and selected that. And that ended up being a Mohican. Really the biggest thing that really drove its selection was this side of it. Having a gigabit Ethernet availability, that just meant, okay, we can start plugging everything in now. And it'll be a lot easier to get things talking back and forth. One of the nice things about this vehicle is that these are variable. They are vectored, but they're variable also. So if we need more power, we can put them all straight forward and drive the machine. When we initially talked to Reson, they said, yeah, we've done dual heads before. And we said, we want 3. And they said, are you nuts? Same with BlueView. We said, we want 3, all in the same machine. They said, really? So what we did is we went to the Reson's facility and got all the sensors together. So we've got 3 7125s, 3 BlueView systems. We had a Tritech sonar, which just came with the machine, and a DVL, because now, same thing, we have to know where we are in the tunnel, and the cable payout was not going to do it for us. So we put them all together and then fired them all up. So we have noise. And so that really wasn't a surprise. And now how are we going to get rid of the noise and how are we going to manage it? One of the, with John Marcus, I believe, from Reson, this is just the quick initial setup. And he was very impressed actually that we did not get as much noise on the 7125s. That worked out very well right from the start. You see the Mantaro, that was ASI's flagship machine that was built back in the 90s with 10 kilometers. And operating systems change every 6 months for a laptop, and that machine was from 97. So thankfully we had the right job to retire it on, and we started with we took the training of the Mohican in our shop facility in St. Catharines, and as soon as was done with the training, we ripped it all apart. So just so we could reconfigure things. So here's the main machine, and this is all add-on material now. So we can start packing all the sensors on. The 7125s, they're in like a Delta configuration out back. The little hole that you see in the bottom here, that's where there's a CDL mini pause nav, INS system. And since this is an AUV-based system, the ICPUs, the computers for each head are resonant with the heads. So took a bit of a gamble on this, and they're all built into one, basically it's a flat pack pressure housing. So that's the machine. We've done, well, we've been back and forth down to Chile 7 times now, and some of those, each trip, sometimes we're doing both sets of tunnels, so we can do up to 3 runs. And so we'll do 3 10-kilometer runs in a matter of a week. So our world record was 10-kilometer runs, and now we can redo that repetitively within a week's time frame. So BlueView systems, they're up front. One of them, the one which we use to look forward with, is actually on the tilt tray with the camera, so we can generally we're looking at the floor, but we can also level with the crown. And the multi-beam systems out in the back. Yeah, you'll see the Tritech chirp sonar, that came with the machine, so we leave it on the back. Just basically it's like a backup camera. We have put another BlueView on the back as well before, and it works really well also. Trying to keep all the information straight and in the tunnel. That's our basic layout. So we're going to have 3 people operating it all the time because there's a lot of screens, especially with the zero visibility, and it's all sonar navigation. So the pilot is sure he's looking at his own console, but also the sonar screens, the imaging sonar, the BlueView side of things, and the multi-beam side of things, and we're logging the data as we go. It's a bit of a blow-up for the BlueView side of things, the forward-looking. The nice thing is when we have this multiplicity of sensors, everything does correlate. You can see there's a bit of call it a niche, or a little bit of an excavation over on the side of the tunnel. That shows over here on the starboard side as well. And we also have the port view side. And this is the rear-facing, which with the Gemini, that's more about, with the Tritech, that is a scanning type system. This is the camera. We just leave it off. We do still use a cable counter as we go out, and that's just our quick general reference as we're making our notes and such. One of the other things with using straight cable payout is that when you have 6 miles of cable, it's amazing how much it really stretches. So we've done 10-kilometer runs before and come back with an extra 200 meters of cable. Over on the multi-beam side, we do use all screens just to be able to monitor each individual head and the data coming back. But this is the general view that we use. So we get that instantaneous 360-degree profile that comes up. This is more the track plot, but this is the multi-beam data as it's being, basically as it's being generated. You can see where that niche is over on that right side again. I always find this is quite handy. This is basically the track plot of the ROV. It's put into the model. It's kind of looks like the umbilical, but it's not. That's actually the course made good of the vehicle. But you can see even with the vehicle wandering, the INS and the software corrects everything, so the data as presented has already been fixed up. The 3D model, that's generated real time as we're going on through. This is great, it's all the point cloud data. We can take that, spin it around to give it a slightly different perspective on things. When we came across this, we didn't really know what the heck it was, and the client wasn't sure either. So it's being able to take that and, next slide, I'll replay it again so we can analyze it. This is all we've got in the way of noise. So running through the tunnel, with all that going on, we've been able really to minimize the amount of noise we get, and sure, there is an awful lot of data cleaning and processing afterwards. This is from the real-time model. We're able to see things immediately, so areas of small relief, really it's just sediment, it's not rocks or anything. It's also, this section is concrete lined, and then from there on up it's more of a shotcrete treatment. So this has got a little extra reinforcement in it. The resolution of the system is quite phenomenal. We're going through one section, and we could see in the data there was a sort of a catenary swoop going on. So we asked the client if they had some cable or conduits in there, and they said, well, yes, by the way, because we have instrumentation in there. So you know how big it is or what type it is, and the rep at the time wasn't sure. We had the opportunity to go back afterwards, and basically the cable's about 1.5 inches, it's less than 2 inches, and we could clearly pick it out with the multi-beam data. It was very, very impressive. Playing it back afterwards, all the data is collected with the PDS software, integrates everything nicely, allows us to play it all back, and then we clean it all up, and then we finally could figure out what that section of the tunnel represented. Presenting it back to the client, it's always nice when you've got this massive set of multi-beam data, but being able to present it to the decision makers. You take the data, we're just doing a side elevation of the point cloud data now and overlaying it on there. This is a rock trap. The rock trap is basically a bunch of holes in the floor. They're designed in so that if rocks do fall out, they'll fall into this trap instead of going down through the turbines and chewing all them all up. So it's fairly important to have a clear rock trap. Well, as you can see, theirs is full. So we've done that repeatedly for them. We can lay them up year after year after year. They can then plan their maintenance, and actually what this is mostly consistent of is sand and silt. So they're not overly concerned with the rocks coming out, but they've obviously got no trap left afterwards. So we've been able to meet those challenges working in the zero visibility all the time. The inspection's done strictly acoustic. We're progressing more and more to making it a routine inspection, and pretty much on the last 4 or 5 runs, there have been no hiccups. If we used to have integration things going on, things would drop out, we didn't have the multi-beams head tuned just right. But now we can go up, set up, and within basically 24 to 48 hours of arriving on site, we're running out 10 kilometers and coming back again. What I want to do is just wrap this one up quickly, was that we've taken that approach and we've integrated that on the smaller vehicles as well. So now we have the robotics. We bought one of the first LBV 300 XLs many years ago, and we said we wanted all the options, and they said, what? So once again, we had serial number 1 basically with everything on it. We had the external thrusters on, additional lighting, everything else, and we bought the basic cable length. And then we redesigned a few things, and we operated over 2.5 kilometers. So that's the longest tether around for this guy. And actually, it was one of the other previous conferences, an INS was on one of these things, and that's a good idea. So we've taken that a step further. We picked up the INS, and this is it's a multi-beam unit. It's a small head. There's only 1 or 2 of them around. And did our SolidWorks design and modeling, and then integrated everything onto the Seabotics now. So here's that nice small compact vehicle, but now it's got INS and 360-degree multi-beam systems on it, as well as we've got a little BlueView tucked in here as well. And it just came back from doing a job where they had to access the tunnel. That's how our access was, through a manhole. And then a little spelunking for the LBV as it got lower down into the shaft and into the tunnel. This is irrigation water, but more, they're turning it into drinking water supply. And it's interesting that they, instead of having just a well, they have a well, and then they started following the aquifer, so they started chasing water. The tunnel's all built by hand. It's quite the system, but they didn't know where it went. So they said, can you come and plot it? So obviously, in that instance, measuring the cable out was not at all what they needed. They said, where does it go? They had a general idea, but they needed it to be confirmed. So that's the plot of it. Here's where we went in. I guess they had started digging for water this way, ran out, they turned around, started digging this way. This is an interesting little feature. This was way before OSHA. So, okay, well, we're about halfway where we want to go now. So if the pumps fail, just dig another tunnel and make it go up. So if the pumps fail, you have somewhere to go. The tunnel's going to flood out, and then hopefully we can get the pumps running and come back and get you. This is a tunnel to nowhere. It goes along and then goes up on a steep slope and stops. So hopefully you can get up above the water line and hang out, and yeah, I know. And hang out long enough until we can pump the water out and come and get you. So that's an interesting feature. This one, they came along, I guess they ran out of water, they came back and punched a little bit more to get some more water. So now they know where it is, and they're using it as part of the whole rehabilitation works. And that's it.